All right, class. Just going to give you another really short video continuing about gravity. Trying to make this as quick as possible. I know you guys have already been watching a lot of videos and listening to me talk quite a bit this week. So hopefully you kind of be able to wrap a lot of this stuff up. But there isn't a lot of neat things to talk about with gravity. On the last video, I think from what you guys would have Tuesday, we left off somewhere around here, where it just explains that, how gravity reduces with distance. As we get further and further from the Earth or a central object, the distance has a inverse square proportion to the amount of force. So that means, if we double the distance like we see here, the force is going to be 1/4 as much. What's the inverse of 2? Is 1/2, and the square of that is 1/4. So distance changes by 2 times, force changes by 1/4. 3 times as much distance, or we have 1/9 as much force. 4 times as much distance, 1/16. 5 times the distance, 1/25. Okay, that's kind of an important idea that we call that the inverse square rule. And that just has to do with kind of how, the gravity kind of spreads out. Light also kind of works this way. Think about you have this central light source here, and as that light radiates out away from the light bulb, the light has a tendency to spread out. And if you look at the area of this inner square compared to the area of this outer square, if you do the math here, the area of this outer square made from the light as it spreads out is going to be 4 times as much as the light that comes through this inner square. So that means that that same light is spread out over this 4 times as much area. That means that's going to be 4 times less, or 1/4 as much intense as it was when it was here. You know that as you get further and further away from a light source, the light gets less bright, less intense. So light, in this sense, works the exact same way that gravity does. We double the distance from here to here, but because it's getting spread out over 4 times as much area, it's going to be 4 times less intense. Much like how gravity, its intensity would be or the amount of force would be one way of looking at it, reduces with distance. So gravity in general, just a few general statements. It's kind of how masses communicate with each other. Gravity exists between any 2 masses in the universe. We talked about Newton's universal law of gravitation. It means it exists everywhere. We already talked. It causes tides, the shape of planets. It causes all of the planets, the stars, all to be round. Okay, it wouldn't make any sense for gravity to make objects become flat unless, high rates of spin or that kind of thing are going on. Falling objects, projectile motion, formation of the solar systems, galaxies, really everything largely is kind of governed by gravity. We obviously know that more mass means more gravitational pull. Most things have so little mass, like me, you, a car, a truck, a building, don't have nearly enough mass to create a lot of gravity. So that's why we don't see, random objects just randomly getting pulled towards each other, because you need a lot of mass to have a lot of gravity. But everything does have some gravity to it. It should also be noted that gravity is a two-way street. Okay, the Earth, the moon is in orbit around the Earth. That doesn't just mean that the Earth pulls on the moon. That obviously means that the moon pulls on the Earth. And this is a guaranteed test question here. Which pulls harder, the moon on the Earth or the Earth on the moon? Now, a lot of people might say, well, the Earth is bigger than the moon, so the Earth pulls the moon harder than the moon pulls Earth. But that would be wrong. Okay, it's a mutual force. The moon pulls just as hard on the Earth as the Earth pulls on the moon. Okay, you drop a baseball. It falls towards Earth. Like, well, the Earth pulls the baseball, yeah? But the baseball also pulls the Earth up by the same amount. Okay, gravity is a mutual force. Both things are pulling on equal amounts on the other object. And as we see here, like we just said, the Earth tugs on the moon tugs backward on Earth. It's a pulling force. The titles here are kind of flip-flopped. This arrow would represent the pull, or I'm sorry, this arrow here would represent the pull from the moon onto the Earth, and this arrow here would represent the pull from the Earth on the moon. Gravity is always a pulling force, meaning it's attractive. It draws things in. So I pull upward on the Earth as hard as the Earth pulls downward on me. You know, you have a large mountain and a small pebble. Both of them have gravity, and they both pull on each other equally. So you might say, well, why doesn't the Earth orbit around the moon then? Because the Earth has more mass. Because even though they're both getting the same amount of force, the same pull, the moon being smaller is going to be more affected by that pull. So that's kind of an important idea to remember as well. So, another short few statements. An attractive pulling force. More mass means more force. Less distance between them means more force, or the opposite of that. More distance means less force. Two very basic statements that we can make about gravitational forces there. Pulls things in. So while we're talking about gravitational forces, it's useful sometimes to speak in terms of gravity as a gravitational field. When we talk about a gravity field, that just means that the area around which that the gravity is acting, the area by which that is affected by gravity. Right now, me and you are sitting on the surface of the Earth. That gravitational field is equivalent for me and you. Even though I might be heavier than you, which means gravity pulls on me more because I have more mass, we're in the same gravitational field. We're experiencing the same strength of gravity on the surface of the Earth. But if I instead went, say, to here, some distance up above the surface of the Earth, that's going to be a slightly different gravitational field. The strength of gravity up here is going to be different than it is down here. And as you get further and further away, the gravitational field up here is going to be, even less. We measured the gravitational field, strength is what we call it, by just speaking in terms of the acceleration of gravity. Near the surface of the Earth, the strength of gravity is 9.8 meters per second squared. That's like the rate that gravity accelerates things. It's the rate that gravity speeds things up around the surface of the Earth. All objects, when ignoring air resistance, fall at the exact same rate. They all fall at the same rate. It doesn't always look that way because things flutter in the air, but if everything was a vacuum, all objects, a paperclip and a baseball, a bowling ball and a paperclip, all would fall at the exact same rate on the surface of the Earth because they're in the same gravitational field. Okay? And the gravitational field acts much the same way as gravity force does. Is that the more the central mass is, the larger the mass of the Earth or the planet or whatever is in the middle, that's this m, is the bigger that's going to be. The larger the distance between wherever we're talking about, and the center of that object, that's squared on the bottom. Okay? So, it kind of works the same way as the gravitational force. But if you just look at this statement over here, if you were twice as far away from the center of the Earth, g, small g, that's the gravitational strength, is going to be 1/4 as much. On the surface of the Earth, it is 9.8 meters per second squared, just like it says here. But if we went to somewhere twice as far, we went, say, 4,000 miles above the surface of the Earth, which is in effect doubling how far I am away from the center of the Earth, that means that the acceleration of gravity would reduce all the way down to 2.45 meters per second squared. And everything at that distance around here would all accelerate back towards Earth at that same rate. So even really high above the surface of the Earth, 4,000 miles above the surface of the Earth, is well into space, it's going to fall back, just at a rate a little bit lower. The ISS, the International Space Station, isn't 4,000 miles above the surface of the Earth, it's only like 220 miles above the surface of the Earth, which is just barely above here. And so that gravitational field strength is only going to be slightly less than 9.8, which, as I mentioned before, that means that the astronauts are going to weigh almost the exact same as they do on Earth. It just looks like they're weightless because they're falling. So, the gravitational field strength reduces with distance, just like the gravitational force does. This really quick is just kind of a fun little side thing. You may have, in the video, like the History Channel gravity video, they mentioned something about this. What if there was a hole dug through Earth? Just a magical, you couldn't do this for a variety of reasons. The Earth is too dense, you know, and just all kinds of weird things would happen. Say, hypothetically, we could dig a hole through the center of the Earth and come out the other side. It's interesting to think about because you would accelerate through that hole. You'd accelerate through that hole. When you got to the center, you wouldn't just stop, but you'd start getting pulled down. But you'd have so much speed by the time you got to the center. You would fly right through the center, but you'd start getting pulled back towards the center. And you'd slow down, slow down, slow down, slow down, stop all the way at the other end. And when you work out the math here, this whole distance winds up taking 42 minutes. The diameter of the Earth is like 8,000 miles. That's just traveling 8,000 miles in 42 minutes just by falling. Okay, so again, you know, oversimplifying this theoretical situation, you'd be speeding up, speeding up, speeding up, speeding up, and then at the exact center, you'd stop speeding up, but you'd be moving really fast. And as soon as you blew right through the center, you'd be slowing down, slowing down, slowing down, slowing down, slowing down, stopping you at the exact opposite side. And weird thing is that this works this way for any path through the Earth. It doesn't even have to be through the center. So if you took a path diagonally like this, say if you went from New York to LA, definitely not passing through the center of the Earth, that magical tunnel, which would have to be dug at an angle, you could fall through it, and it would take 42 minutes. You could dig a tunnel to, I don't know, Columbus, 42 minutes. You could dig one to Avon, 42 minutes, which obviously wouldn't be beneficial to you, but is interesting to think about. And again, it's, at those shorter distances, wouldn't really be a tunnel so much as like an incline that you're rolling down. But weirdly enough, that's just kind of one of those things. So you could have this kind of gravity tunnel where you fall through Earth, and you'd feel weightless the whole time. But it's just to think about where you'd be speeding up and where you'd be slowing down. This is a video that will be played separately, just you know, a minute physics things, like 3 minutes long, if you guys have time. So, a few hypothetical questions. So, here's a person standing on the surface of the Earth. We're just going to jump this to full screen here. So, you have a person standing on the surface of the Earth, and say, as we did that, the Earth magically shrunk, but you stayed in the same location. So the Earth had the same mass, but it all shrunk down in the same location. What would happen then? What would happen to the amount of gravity acting on you? Would the force of gravity acting on you there increase, decrease, or stay the same? Now, the amount of gravity acting on you depends on your mass, the Earth's mass, and the distance between their two centers. In this kind of ridiculous hypothetical situation, none of those things changed. None of those things changed, so that means that the force of gravity on you wouldn't change. So it would not be changed. Your mass, the Earth's mass, and the distance between their centers did not change. So in this hypothetical, the force of gravity would be no different. Second hypothetical, say you were up here on the surface of the Earth and the Earth shrunk down and you stayed on its surface. What would happen then? Now, the distance between you and the Earth's center reduced by a lot, even though your mass and the Earth's mass did not change. But because you are now much closer to the Earth's center, and all of the Earth's mass is still underneath you, that means that, that your force of gravity would increase by a lot, because the distance between your center and the Earth's center would decrease, which means the force increases. Okay. Another thing here. Sorry. Now, so gravity, as we already mentioned, is a two-way street. It's a mutual tug of war. So take the Earth and the Moon system for a second. Each are pulling on each other. The Moon orbits the Earth. But technically, the Moon doesn't orbit the Earth. The Moon enters the center of gravity, the center of mass between the two objects, which is like here. You would think it would be like here, but it's not. But, you know, it's kind of like, imagine this hammer thrower, which is like an Olympic track and field event. This guy's swinging around this big weighted hammer, and it's going in this big wide circle. But this guy's kind of going in a smaller circle. because he's orbiting or circling around the center of mass of those two objects, and that would be here. That kind of fake center is what we call a barycenter. So it's an 81-to-1 ratio for the Earth and the Moon. But the Moon is actually orbiting its axis, its center point for its orbit is actually here, somewhat outward from the center of the Earth. It's going to be the center of gravity of those two objects. And they both orbit a common point in space. If the Earth and the Moon were the same mass, that point would be in the exact middle, and they'd both be orbiting around an empty point. It would be called a binary or a mutual orbit. It's a better visualization of maybe the same thing. Here's the Moon's orbit, here's the Earth, and this X marks the center of that orbit. Again, very clearly not in the center of the Earth. Again, that's called a barycenter. Another new term, just very quickly, kind of a funny sounding term, is perturbations. All the planets orbit the sun because they're kind of trapped, they're locked in with the sun's gravity. But the planets, some of them at least, are pretty big. And so they have a tendency to kind of tug on each other. Those tugs create little irregularities in the planet's orbits. And we call those irregularities perturbations. This is actually how we discovered Neptune. On the solar system chapter, I mentioned that that Neptune was the first planet that was predicted before it was ever actually seen. We did that because we noticed that something was tugging on Saturn and Jupiter and Uranus, and all those things kind of made their orbits be a little bit weirder. So we did the math and did the calculations, looking at the gravity of it, and we discovered Neptune. So we discovered Neptune by looking at the perturbations its gravity caused on the other planets. So all the planets, they're close to each other at some points and far away from each other, and they have a tendency to kind of tug on each other, as you might expect. That tugging and those irregularities caused by that, those tuggings are called perturbations. So there's another new term, kind of a funny sounding one. So here's some fun stuff. I touched on this a little bit the other day, but there's a difference between being weightless and feeling weightless. Okay? The term weight is a synonym for gravity, for the force of gravity. Weight and the force of gravity mean the same thing. It's how much gravity is pulling you downward. Now, sometimes you can feel weightless. You jump up on a trampoline, you're up in the air, you feel weightless for a few moments. But that doesn't mean that gravity stops acting on you. Okay, you can feel weightless all the time. Jump up on a trampoline, jump off the side of a building, go skydiving. You can feel weightless. Astronauts feel weightless, but they're not actually weightless. The example I talked about the other day was an elevator in free fall. In that elevator, you'd be floating around. You'd be Peter Panning your way from the bottom to the top and be able to float around the room the entire time that was in free fall. But that doesn't mean that gravity's not there. It just means that nothing is holding you back up. Being weightless, you can't really be weightless anywhere even close to being around the Earth. You can't really be weightless anywhere because gravity extends throughout the universe. There's not really anywhere where gravity does not act. So as we see in these GIFs here, that you see some examples of people looking like they are weightless, like they are feeling weightless. We'll come back to the second one later. This is a snippet of a kind of a neat music video that was actually made. This, weirdly enough, I think is a snippet from an episode of The Bachelor, but that's just the first one I could find. So, astronauts in orbit, like this guy. He's not even in a spaceship. This is a guy in an actual spacewalk around the Earth. He's in orbit. He's going as fast as the International Space Station or his space shuttle is. He is out there floating around. He feels weightless, just like, people that are in the space shuttle. But, that just means that they're in a continuous free fall. They feel weightless because nothing's supporting them. But if they were actually weightless, if there's no gravity acting on them, they would fly away from Earth and never come back, and we would never see them again. Gravity is what keeps them around the Earth. As long as gravity is still acting, you cannot actually be weightless. So next, I'm going to stop this recording and have you guys click on the next link on the calendar and it's going to be this music video. If I try to play it on here, it would show up weird. But it's an actual music video, and we'll show the video for how it was made as well. But all this was actually shot. This isn't like computer animated. This isn't you know, CGI or anything like that. This is actually shot. These guys went in one of these planes, sometimes referred to as vomit comets, that go on these big parabolic arches, up and down, up and down. And it creates about 20 to 30 seconds of weightlessness at a time, followed by several minutes of feeling heavier. So you feel weightless, but only for 20 or 30 seconds at a time. Because for each weightless amount, you have to you know, go through several minutes. You know, it goes through these kind of parabolic arches here. We see that here. You know, here's a plane. Here's the path the plane takes. It's kind of scooping you up. And up here is when you feel weightless. It's kind of tossing you up. And you feel weightless about 25 to 30 seconds, and then you start falling down. So then you have, you know, a longer amount of time where you're feeling heavy and you're feeling gravity again. You've got to wait for it to get to the top of that next hill. So the question is to you, as you guys watch this, is how could they have shot this? Because it seems pretty continuous. It's like 3 minutes of them more or less being weightless. So how did they continuously shoot this while they're only could get 20, 25 seconds of weightlessness at a time? So I'll stop this video now, and you guys can go to the second link on YouTube and play this video by the group OK Go. They're known for kind of making really kind of cool looking music videos. You can play that. And then after that, play the how it was made video, which will be the next link on the calendar. And it's kind of interesting how they use one of these planes. It was actually a Russian, you know, zero gravity type simulator. It's actually similar to what you saw in the History Channel video yesterday. So I'll stop this now. Watch this and enjoy. First watch the music video, then watch the next link where they explain how they made that and relate that to what we're talking about that aspect of feeling weightless. These people are all on Earth. They're not deep in outer space somewhere. They have gravity the whole time, but it's that repetitive usage of creating simulated zero gravity. So watch and enjoy the next link.